Welcome everyone, welcome those online to the first Euclid webinar. During this webinar, which is divided into two parts, we'll focus in the first part on an introduction and overview to the semantic web technologies that are used underlying linked data. I'll take a quick look at the Twitter stream to see if there are any questions to be answered on that first part. And then I'll continue for the second part to talk about linked data itself. Both what this means in terms of principles and best practice, and in terms of what some of the examples are out there of linked data being used on the web. At any point during the presentation, if you're watching this live, you can tweet your questions to the Euclid Project Twitter channel. Okay? We're also very happy to receive your questions and your comments offline if you're watching this streaming. So without further ado, let's continue with the first part of this agenda, which is the motivation scenario for Euclid as a whole in terms of the training material that are going to be presented on data production, exposure, and consumption. The scenario that we've chosen to go through this whole set of webinars is based on the music domain. So there's several parts of content that have a data component that we're going to show how we can bring together using semantic technologies and a linked data-based approach. So obviously the first part is the musical content itself. On the web now, or on the internet in general, there's a lot of music available by legal means now, both in streaming form and download form. So both, for instance, downloading from iTunes, listening online to Last.fm, to Spotify. Underlying this kind of content, there's a lot of data which we would term metadata because it disambiguates the musical content. So we have information on the music itself, on the artist that produced it, by extension on the labels and producers that were associated with particular releases. Okay, there are data sets that pick this stuff up and already publish some of that as linked data. What you also find out on the web, which we'll concentrate on later when we talk about mining, for instance, is content like review content, where people go to a new single or a new album and give their reviews. Now, some of this exists somewhat within the linked data domain, so some of it is interlinked with the metadata. Some of it's not. Some of it's just web content at the moment, primarily web content. And as I say, we'll discuss when it comes to mining how we can aggregate this stuff together. The fourth kind of content, just to mention, we might also have visual content associated with these things. So album covers, artist pictures, these kinds of things. If we want to build a music-based portal, and if we want to use linked data technologies to help us do that, okay, it's the linked data, it's the identifiers, it's the interlinkage that's going to help us pull this stuff together in a low-cost way to make such a portal. We've an architecture diagram that we'll come back to later, in later webinars, to talk about how all of these different kinds of content are scraped, are brought in-house, linked together, and used to make a portal. That's just kind of a forward reference for later webinars. The expected results, as we'll show as we talk about these different technologies used, are both easily assembling such a portal as web content, but also contributing back into open linked data. Okay? We're going to talk about how it's necessary to improve across these different kinds of content on interlinkage, especially concentrating on artists, bringing together reviews and visual content, and we're going to discuss along the way how some of the existing large web-scale adoptees of this kind of linked data technology can be addressed in quite a simple way. So, for instance, through Google Rich Snippets, although that's recently renamed, Facebook Open Graph, and Schema.org. So for things like the social web, for searching across the web, we'll show how linked data technologies can increase the prominence and usefulness of such a portal using linked data. Okay, in order to get there, we need to first talk, the real subject of this first webinar, about the underlying technologies a little bit. Now, everything assumes, even pre-web, that we're talking about an internet context. Okay? Two things that it's useful to know about that is that's not just a communication mechanism, it gets data from point to point, but that every host on the internet, the way that the internet protocol works, is by the assignment of internet protocol numbers. In most of the existing internet, we're talking about Internet Protocol version 4, where you have four numbers chained together that will identify a machine. That space is expanded more recently with Internet Protocol version 6, but fundamentally that's what's happening. You have each host has a number by which it can be addressed, and then throughout the infrastructure there are routers that understand different routes to communicate data between those hosts. And it's no surprise, it's no big news to say the use of this protocol to connect machines has increased very rapidly over the decades. In recent years, it's really third generation and fourth generation mobile telephony networks that have increased that rapidly. And we'll also touch on that when it comes to the motivating scenario, how one can make mobile interfaces and how people have out-of-link data technology. Now, while the internet's existed for all that time and has proven useful on a technical level to connect machines, the real opening up of internet technology to the general public was when an interface was put on top called the World Wide Web. This is now how most people transact most of their interest and business on the internet. While there's a massive amount of information available out there on the web, which is increased even more by participation, by production of content, by pretty much anyone that has an internet logon. So we look at sites like Wikipedia, where anyone can contribute, where anyone can edit. On the other hand, the technologies that are used there are very oriented towards human intelligence. So if you want to find something, if you want to understand something, and especially the motivation here, if you want to extract and aggregate information that you can find at different points on the web, it's very much a manual task. It involves a lot of human understanding using the original web technologies. So if we find various sources out there on the web, want to find where the relevant documents are to pull out content and combine them in meaningful ways, a better alternative than just doing that with human power on an individual basis is to move to something that has been called the web of data, where we use semantic technologies to explicitly expose what the data associated with content on the web is. Okay? And all of the technologies that I'll talk about going here forward in this first webinar are technologies that can be used to realize that idea of a web of data. But one important caveat before I say what they are, none of the technology that we talk about is useful only predicated on having an entire web of data, of somehow replacing the whole web with a web where explicit data is associated with all of the content. One, this stuff is useful even if only some of our sources have explicit semantic data to start with, which we'll talk about in the music portal. And two, even without making applications in an open way where we're exposing data, this technology is useful. So these can all occur just as we form intranets out of web technology. We can also form enterprise-specific architectures using semantic technologies that are useful within boundaries, that are not necessarily exposing data. That said, exposing data when you have the ability to do so helps create impetus, create critical mass for it to be more and more useful to use these technologies to combine and understand data. We can see a kind of evolution across what I was just saying now from pre-web internet technologies, some of which we'll touch on, through the two standards, which we'll come to next, that make the World Wide Web, the transport mechanism, HTTP, and the document encoding, HTML, okay, through this to Web 2.0, where we start talking about technologies like wikis, enabling people, and web services also, enabling people to produce as well as consume content more easily in a standardized way, through to the use of that, one in social networks, and along another dimension with these semantic technologies with explicit exposure of data, and then ultimately to some future vision of intelligent agents acting on our behalf across that kind of data, across that kind of network. Okay? Now, that futuristic vision at the very apex of this diagram, as I said, is not a precondition for making useful use of the semantic technologies over here. So we'll talk about RDF, the resource description framework, its schema language, the associated ontology language, and the query language Sparkle. So that it's a protocol and RDF query language that can be used across aggregations of this data. All of that stuff's useful without getting into this future space of agents and intelligence out there on the web. Okay, so the two technologies that I just mentioned that are the basis of the traditional web. Okay. On the one side, we have a means to describe our documents in a way that's useful to display them with formatting, with inline pictures, and in more recent versions, audio and video content. Okay? But fundamentally, with hyperlinks between documents. So documents link to documents and let us navigate across the web. The way that documents link to one another is by being addressable, by having identifiers that are called URIs now, Uniform Resource Identifiers. And given a URI, which is one built for the web that uses the Web Transfer Protocol, HTTP, HTTP will tell us how to have a conversation with the server using that identifier to request some form of the content, some representation associated with a resource, to retrieve that, and in the simple web case, where that will be an HTML representation, we can both have the content displayed for us and find hyperlinks via URIs to more content that we can request using the protocol. Okay, so some examples of URIs which are not restricted to be HTTP URIs are, for example, we can make a complex identifier using the LDAP directory protocol. Every internet email address can be encoded as a URI. Okay? A pre-web mechanism for exposing narrative content and linking it to one another, the Usenet, can be URI. Each document within the Usenet can be URI encoded. Okay? Now, what's in common between all of these and others that I'll skip over is simply that each one contains a colon. Okay? Before the colon is the name of the scheme. Okay? What kind of document is this, and how should you go about getting it if you can? Okay? So, using, for instance, Usenet, we can talk to a Usenet server. Okay? So similarly, in HTTP, before the colon, the scheme name says this is an HTTP identifier. You can talk to an HTTP server to get the identified content. And in that scheme, we expect that what follows the double slash before the first following slash is an authority. Okay? It's the owner of the content. It's also resolvable to an IP address mentioned earlier to have the HTTP conversation to ask for the content. And what you ask for is what follows that slash. That's the identifier relative to that authority. Okay? Now, I mentioned it's only in some cases the scheme will tell you how to talk to a server and let you actually retrieve the content, because there are plenty of schemes that don't allow you to retrieve the content. They just identify something, identify a resource, we say. So, for example, we can explicitly say that this thing is a uniform resource name, not a uniform resource locator, and say, we don't tell you how to retrieve this, but here is an identifier which everyone should agree on. Okay? Now, if we want to describe data, which is what we're doing in linked data, in general, we have two concepts by which we arrange our resources. One is the relationship. Okay? So on the web, we said documents that have identifiers have hyperlinks to other documents. But those are essentially ambiguous relationships between those documents. While we might try using graph algorithms, as Google do, to try and understand what the network of links between different documents means, fundamentally, we don't know. If I link to something, I could be agreeing with it, I could be refuting it, I could be saying this is further information of a specific kind relative to my document. And a hyperlink doesn't tell me. It doesn't say what the relationship is. So the first thing we do in the resource description framework in a semantic world is to attach relationships to the links between resources. Okay? The second way that we understand our data is to group resources together into what we call classes. Okay? So we say all of these resources within the class share something in common. Okay? So the class itself is a resource that groups resources. The relationship is a resource that disambiguates these links between other resources. Now, the means to define what relationships we understand and what classes we understand, in general, we would call a vocabulary. As we go forward, we'll see that a vocabulary can be defined either by a schema or by an ontology. Ontologies being richer than schemas. But in both cases, we can just refer to that thing, either a schema or an ontology, as a vocabulary. And the vocabulary will tell us these are understood relationships and these are understood classes. So some vocabularies that are well used in describing data out there on the web, now the web of data, we have the friend of a friend vocabulary, which will give us classes like person, the group of resources that represent people. It will give us relationships like knows, that we can use to specify the relationship between two resources representing people. So if I know someone, I can represent myself with a resource, represent them with a resource, and relate the resources using the knows relationship. Okay, so another commonly used vocabulary is the Dublin core. The Dublin core, while it existed before the resource description framework, RDF, is now well used in RDF and lets us attach general metadata, in particular to things that are works, that are things that people produce. So we can say this is the format or the media type of a resource. We can also say the creator to this resource is represented by another resource. For instance, one that's in the class of people according to FOAF. So we can mix these vocabularies up. Okay. Another vocabulary, SHOC, the semantically interlinked online communities vocabulary, will let us talk about things that people write like blog posts, like what we call microblog posts. So for instance, tweets. If you're tweeting during this webinar, we can encode your tweet using SHOC to say that that resource that you've created by tweeting belongs in the class of microblog posts. We might use Dublin core to say that it was created by a resource, and we might use FOAF to say that resource, the creator, is in the class of people, and we might attach metadata to it, again using FOAF, like your name. An ontology, so a rich vocabulary that we'll see more of as we go through these webinars, is the music ontology. So certain domains have domain-specific vocabularies associated with them. So when we're describing music, we might use this one very often used, but not necessarily exclusively used, vocabulary called the music ontology. Finally, I want to mention what we'll cover just from the point of view of using it as a vocabulary, not using it as a model, which is also useful, but less part of what we'll cover during this course, is SCOS, the Simple Knowledge Organization System. So it lets one build models, especially taxonomies, in a slightly different way to RDF schema and OWL, the ontology language that we'll talk about. But as a vocabulary, it gives us some classes and relationships that are useful to us in general terms. So, for example, we'll talk later about attaching particular kinds of labels to things. So in general, in RDF, we'd like to attach a human-readable label to our resources to understand them. SCOS gives us some useful vocabulary to say there's one preferred label for a resource, but there might also be alternative labels that are synonyms for that resource. Okay, if we want to find vocabularies because we're encouraged to reuse them rather than reinvent classes and relationships, we need ways to find them. So a useful way, or a bunch of useful ways to find vocabularies are here. One is to go to the W3C working group on creating linked open data. Okay, so the people who've pushed this movement forward, exposing open data using linked data technologies, also maintain a good list of vocabularies that can be used there. We can also go the other way and leverage described data sets that are aggregated, that are cataloged by means we'll talk about later, and use linked data to describe those data sets and the vocabularies that they're using. Okay, so a project called Linked Open Vocabularies does exactly that. It says, here are vocabularies that are used in those open data sets, rather than just that are encouraged and self-documented in a human way. I mentioned that specific domains, so specific areas of application, also have specific vocabularies associated with them, as well as the use of the generic ones. So you can also go to that community. So we give the example, if you're interested in library-oriented catalog data, you might go to this working group for a list of vocabularies that are used in that domain. Now, when it comes to building these ideas up into a technology stack and a language stack, the diagram that's often shown is this one. Okay? We build on top of the kind of web technologies that I briefly mentioned, so the identifiers that we call URIs. There's also a movement towards better internationalization support using Unicode character encoding. And there's the idea of having data formats that abstract from the ideas that HTML took from the earlier SGML that we call XML. Okay? We will use XML to allow machine-to-machine communication of data. We'll use URIs to identify everything, all of the resources that we describe, and both informing those URIs and informing things like labels that we attach to them, we'll use Unicode. So this stack is well grounded on top of the web stack, but these technologies are novel to semantics. And the first one that we'll look at is the Resource Description Framework, RDF, which I mentioned. It gives, on top of XML as one way to transfer those descriptions, a basic data model for descriptions of resources and their relationships. On top of that, I've mentioned a simple means to build vocabularies to help communicate what that understanding of resources is. is using RDF's schema language, or RDFS, a richer way to describe the classes and the properties that we use to describe our data, is the ontology language for the web, or the web ontology language, or in one more permutation, OWL. Okay? So the ontology language for the web is called OWL. I also mentioned in passing what we'll touch on in this webinar and follow up in the Module 2 webinar in much more depth, which is the query language for data that fits this RDF model. So we call it both protocol, the P part, so how do we talk to people who allow these queries, and what do we pass, so the RDF query language, the RQL part. On top of that on the stack, we have things that go more into the research domain that aren't leveraged so much, at least yet, in linked data, and that aren't so much topics for the Euclid training. So we'll pick the first of these, as I said, the resource description framework, and look at that in a little more depth to start with. Now, the resource description framework, we've already mentioned, resources are identified with URIs. That's the scheme that we have to point at particular resources in the collection, which can be as big as the web and can include our private enterprise silos of data. Okay? Now, each of these resources can be involved in relationships, and RDF is simply a way to communicate those relationships between resources. Okay? So in every relationship, we say we have a subject and an object. These are the two related resources. You have a relationship from the subject onto the object. Okay? But unlike on the web, where we just have a hyperlink from one document to another, in RDF, we have a link from one resource to another that has specified what the relationship is. And we call that specification a predicate. Okay? Now, in general, it can be that all three parts of this relationship we specify using URIs. We use a URI to identify the subject, we use a URI to identify the object, and we use a URI to identify what the relationship is, so what the predicate is. Now, we call each statement or assertion that we make using RDF informally a triple, because it's got these three parts always. It always has a subject, a predicate, and an object. So here are two examples. We have a URI from the Music Brains dataset that has lots of metadata about music. So the subject, which in the language we're encoding here, a URI goes between angle brackets. So far, just to mention, these are specified in N triples, but they're also valid in a more useful language, more readable language called Turtle, the terse RDF triple language, which is what later examples, that's the syntax we'll use. That's always the syntax that we'll use on a slide, because it's the recommended syntax for RDF to be read by humans. Okay? So we have the subject. It's a URI in angle brackets. In the third part, we have the object, which is the same, a URI between angle brackets. And what we're asserting with this statement, with this triple, is that there's a relationship between these two resources. The relationship is also specified with the URI, again, because we have angle brackets. And if we read it, eventually we get to a point where we spot that this is using OWL, using the ontology language, and in particular, following the hash, we see that the local name for this relationship is same as. Okay? This is a way of specifying that what's identified by this URI from the Music Brains authority is actually representing the same thing as this URI from DBpedia. Okay? And a particular characteristic of DBpedia URIs is the local part of the name there is useful in understanding what that resource represents. Here, in particular, it's the Beatles. Okay? So we have a URI in MusicBrainz that one couldn't really read. One can read so far to see it's something, it's some resource that represents a music artist, but the long part of the name there with what's called a UUID is not readable. Okay? On the other hand, it's representing the same thing as the DBpedia one, which is recognizable, is readable as the Beatles. And we'll talk about the trade-off between these two ways of identifying things, and also the fact that some of these URIs use hashes before the local name, and some just use one more slash before the local name. Okay? There's trade-offs between the two of those, but what to understand for now about this triple, about this statement, is it says this URI represents the same thing as this one. Okay? Now, we have a full stop to mark the end of that triple, and we have a second triple in the same syntax. So the angle brackets mean we're talking about a URI identifying the subject, which is actually the same subject as the first triple. The relationship is a different one. Again, we can read through it and guess we're using the FOF vocabulary, and the local name of the property that we've taken from there is name. So we're giving a name to the resource. Okay? When we give names to things, we don't want to link to another resource with a URI. We actually want to give the name as text in the object to that statement. That's what's called a literal, again, because we inherit from XML. They have a lot of the same characteristics as literals in the XML world. In this serialization, in this representation, n-triples, which is part of Turtle, we put quotes around text. Okay? So the angle brackets means this is a URI. I'm giving you the whole URI for this part of the relationship, for this part of the triple. The quote marks means I'm giving you a string, a piece of text as that component of the triple. So we give a name to that MusicBrainz identified resource, which is the string The Beatles. So this is another way, actually a better way, to find out what the name for the resource is than relying on having URIs that we can split up and try and understand as we read the Beatles. Okay, now every triple, again, just to go back to those two, subject, predicate, object, three parts, we call these statements triples. Every one of those statements can also be drawn. Okay? We draw an arrow from the subject resource to the object resource in a graph, and we use the predicate to label that arrow to say what the relationship is. Now, by using URIs as global identifiers for resources, we can share our descriptions and combine them in understanding the data that we've encoded as a graph. So, given those two previous statements, those two previous triples, you can see in the serialization, which I mentioned at the time, they share the same subject. They have the same URI for the subject. Now, I could have written both of these triples, or I could have got them from two different sources. But the fact that we use URIs to represent things like the Beatles mean that we can combine these two triples into a graph, which is what happens here. Okay? Both triples have the same subject, so both of the arrows that they form in the graph have the same source, which is this MusicBrainz URI for the Beatles. Then you'll see each of those arrows has different labels because we were talking about two different predicates, two different relationships that this resource representing the Beatles has. One was the same as relationship, one was the name relationship. Okay, so two different predicates label the arrows. And under those relationships, we have two different objects. One object is the DBpedia identifier for the Beatles, The other object is the literal string, the piece of text that says the Beatles. Okay? So 2 triples lead to 2 arrows in the graph. And where we share URIs between people, then across this entire web of data, we can aggregate at the nodes in this graph. So we say some things talk about the same subject, some things talk about the same, some triples talk about the same object, so lead to arrows going into the same object. Okay? And in that way, we form a simple graph, technically a labeled, directed graph, of all of the data that we can aggregate together, or that we're interested in aggregating together, from RDF statements. Now, there's one caveat to this idea of forming graphs which connect identified resources, and in which some cases we can have literals as the object to arrows. By the way, not the subject to arrows. We can't have any arrows coming out of this string for the Beatles, but we can have arrows going in. Now, that doesn't completely describe the kinds of graphs that we can form, because RDF allows us to have something called blank nodes. Okay? These are parts of the graph where a particular node doesn't have a URI and isn't a literal. Okay? So it doesn't have these don't have the restrictions of literals. You can have multiple arrows coming out of a blank node, but the blank node doesn't have a URI. It doesn't have a shared identifier, okay, that would let other people also talk about that node in the graph and make new statements that lead into it or that lead out of it. The reason sometimes we have such nodes in our RDF graphs is to group together information, so we need multiple arrows coming out of that node, but we don't want to name it, we don't want to share it. Okay? One reason to do so, we can see using this vocabulary called WGS-84 for World Geodetic System, as standardized in 1984. It's a system for giving geographical information to resources. And in particular here, as well as saying that this thing is a point, which we'll come to later, we say this thing that doesn't have a name has a latitude and a longitude, okay, given in literals. Okay? But those two relationships both come from the same point, but it doesn't have to be given a name. Okay? But just as it can be the subject to many relationships, it can also be the object to a relationship. So I could say, I'm related to this unnamed resource because it's my home base, that it's my location at a given point in time, all kinds of interesting relationships, even without naming that node. Just a caveat to that, in general in linked data, people are cautious about introducing too many of these blank nodes. So this would be discouraged, at least unless it's necessary. Now, coming back to how we write down RDF, you'll see in the two triples that I gave you before, we had the same subject, and it was a bit repetitive. I was writing these very long URIs multiple times. The terse RDF triple language, Turtle, will let us make two shortcuts. Okay? We don't have to write the entire repetitive part of different URIs, but in the same scheme, out over and over. And we don't have to rewrite when we reuse a resource, say, as in that example, as the subject of more than one relationship. So it's all about cutting down the amount of repetitive writing we're doing. So the first idea, again in common with XML, is to say where we have a scheme of URIs that has different local names, in other words, just the bit after the hash or the slash is changing, we call the start of that, the repetitive part, a namespace. And we introduce what's called a namespace prefix. So we give a very short name to this repetitive part. So instead of writing all the time this whole part of the URI for things in the RDF scheme and putting the local name on the end inside brackets, We just say the repetitive part has a prefix, has a short name, RDF. The same for RDF schema, the same for OWL, and the same for things that other people have defined for non-standards, okay, like the music ontology, like DBpedia resources. Okay? So instead of rewriting these namespaces over and over, we give them a short name. Now, in a Turtle document, we can have multiple prefixes for different URIs. We can also have one, what's called base, which is like a namespace or the start of a namespace that we'll use for everything else. Where we don't nominate a prefix, we can also shorten the URIs within that one unique base scheme. And we'll see some examples later to explain the difference. So in the running examples here, we'll give a base to the document, which is this part of the Music Brains scheme. Actually, my apologies, that shouldn't say artist. So what we want to do is use the base of musicbrains.org and then just / as the base to the documents. So here's an example using that language, which generalizes N triples. Again, just to remind, this is called Turtle. So we introduce a base, and here it's written correctly. We're saying the base is musicbrains.org /. Okay? We have a prefix for the music ontology, and then we specify a triple. But while we've put angle brackets around the subject, that's specified relative to the base. So we glue the base on the front of these things inside angle brackets now. So we don't have to write musicbrains.org over and over. Okay? For skipping the predicate, let's just look at the object. For the object, we've reused this prefix for the music ontology. So the local part of the name is music group, and we stick that after the / with all of this before for the music ontology to get the URI for the object. Okay? Now, one thing worth mentioning that distinguishes bases from prefixes, what goes after a prefix can just be a local name. What we've allowed ourselves to do by using a base to specify the subject is actually have a path or a partial path that's glued on afterwards. So we can have artist / and then the UUID and then #_. So the local name for this resource is just an underscore. But we can have this glued on after the base, informing the URI. So with base, we have more flexibility to put more after the common part that you glue, but uniquely for the document. We can have several prefixes, but we only have one base. Now, this triple expands into something, again, that's valid Turtle, but that also is valid in the restricted language N triples that we were using before, to this statement. Okay? Subject, predicate, object, with no bases, with no prefixes. Okay? Everything fully written as URIs. Now, we've said it's clear how we expand the subject. We put this within the brackets after the base. It's clear how we expand the object. We pick the particular prefix that we've nominated, the music ontology one, and glue music group afterwards. Okay? Now, there's one more shortcut on this slide. The predicate in Turtle is just the letter A. We read out, this particular artist is a music group. Okay? Is Turtle's shorthand for that relationship that puts resources into classes. Okay? So we understand that music group is a class of resources, a grouping together of resources that share something in common. Okay? Just by reading the URI, we could probably understand what that class is meant to represent, that all the resources in the class are music groups, like the Beatles were. Okay? Now, that shortcutted predicate, the letter A, expands to a particular predicate from the RDF scheme. Okay? That's the local name for the predicate is type. Okay? So we might commonly also have introduced a prefix called RDF for the RDF scheme and said the relationship is RDF type. Again, that's a particular predicate for putting resources into classes, and we'll use that again and again. Because it's used so many times, Turtle lets us just use the letter A to represent that predicate, that relationship. Okay, now here's the other contraction that Turtle lets us make. We're talking about understanding the base and prefixes that we had before. We want to assert the same two relationships that we had in the graph that we specified in n triples, but not just using the base and the prefixes to shorten the way that we write URIs. We also don't want to repeat the subject that we're using multiple times. Okay? So we have one triple, which is the MusicBrainz URI has this property called label from RDFS to give it a name, where the object is this literal, this string. But instead of putting a full stop, as we had to in n triples, to say we finished that triple, we'll start another triple, we use a semicolon to say we're still talking about the same subject. Okay? So still talking about the same subject, we give another predicate, another relationship, which is same as from OWL, which we saw before. And an object, the first object to that, is the one that we saw before, DBpedia's URI for the Beatles. But again, instead of using a full stop, and instead of using a semicolon, which would mean now we're going to talk about a different relationship for the same subject, the comma says we're still talking about the same subject and the same relationship, the same predicate. We're just going to give another object to that relationship for that subject. So having said first that this URI identifies a resource representing the same as this URI, the DBpedia one, we also say here's a third URI in a BBC scheme that also identifies the same resource, understood as the Beatles. Okay? So, triple, the second triple assumes the same subject, so this URI, same as DBpedia, and then the comma says a second object to that same relationship. So this URI is the same as the one that the BBC use. One more interesting thing, useful to know about, especially for querying in the next module, that Turtle allows us to assign, and indeed n triples allows us to assign, some further disambiguation to these literals that we're attaching to resources, to these bits of string. So in general, a literal is just a piece of text. We can attach one of two tags to that to help us understand what kind of text it is. Okay? One of them is very useful for machines to help us interpret what that text is, which is to attach a data type. And in general, we would reuse the data types from XML. So XML schema has an addendum which discusses data types and how to encode data of particular types in text. So to this URI, again, assuming the base of musicbrainz.org, we have a URI which is a kind of recording with a UUID. We put it into the class of signals, a class defined by the music ontology. And then we say, semicolon, still talking about this recording, we give it a label. So here, just a plain literal, just a piece of text. But then we also say, for this subject, we have another relationship called duration from the music ontology. And there we attach a literal, but we attach a tag to it. These cat's ears, the double caret, means this is the data type that follows. So relative to the prefix for XML schema data types, we say that's a kind of duration. So duration as a data type is attached to that literal. And XML tells us how to encode durations in time as text. Okay? So you can actually read in here the three, after the prefix, the 3M48S part means that this recording lasts for 3 minutes and 48 seconds. Okay? The way to parse that is just as XML tells you to parse it using that data type. Okay? Useful for machines. Okay? Another type of tag that's useful to add to literals is more oriented towards humans, at least helped by machines. Here we have another URI for the Beatles. We know it's just another one because of the same as relationship that we had before. So the Beatles have a relationship that the DBpedia ontology calls abstract. We can attach an abstract to something, not just a label to it. Label, a short bit of identifying text. Abstract, some longer text about it. So the first object in this relationship, subject, predicate, object, is this literal that starts with the Beatles were an English rock band, blah, blah, blah. Okay? We add a tag to that which uses the ISO country codes to identify languages. So we say that text can be read in English. Okay? Then we use a comma to gather another object to this abstract relationship relative to the Beatles resource, and we write out a bit of text which the language tag says can be read in German. I won't embarrass myself. So, we have talked about the very simple language to write down RDF triples, N triples. We've talked about the shortcuts you can make in a language called Turtle, which make it quite readable to humans. We can also encode RDF triples in a language called RDF XML. Now, I said before, XML is a useful way for machines to pass around data, partly because you get generic parsing implementations for XML. Now, the point is not to teach you about how to read or write this, because in general, I would say you shouldn't. You should read and write the Turtle language, okay? But there are completely generic tools on and offline to let you translate any document from Turtle into RDF in XML and some other serializations that exist for RDF too. So if you get RDF in XML, you can turn it into Turtle and read it. If you've written some Turtle, you can equally, just automatically, without thinking about it, transform it into RDF in XML if that's what a given tool, if that's the only thing that a given tool will support. Although increasingly, the tools support Turtle now. It's on its route to standardization as a recommended way to read and write RDF. Now, to continue the story, I should tell you a few things about the RDF schema language. Okay? As I said, schemas are a simple kind of vocabulary, and a vocabulary tells you classes, so the resources that group other resources together, and properties, so resources that are used as predicates to specify relationships. Now, there's two ways to read a schema document. One is just that. If somebody uses this vocabulary, what is my expectation for the kinds of things that they talk about, so the classes of resources that they talk about, and what is my expectation of the properties that they use to specify the relationships between resources. Okay? So the classes and properties in a schema can be read as, these are the kinds of things and the kind of relationships that you talk about using this particular vocabulary. Okay? But they also have another side, which is inference. If you can say, I intend this class to be used in particular ways. I intend this property, this relationship to be used in certain ways, so that when it is used, you can infer things, even if they're not explicitly said, even if there isn't a triple to encode certain things, the machinery, what's called a reasoner, can derive triples from the triples that have been asserted together with the schema. Okay, so we'll take a look at those in a second. To start with, let's introduce an example. So in the music ontology, we have a property that's used to specify relationships called member, okay, which relates a music group to people who are in that group. Okay? Now, the first thing we do, if we want to explicitly say that this resource is a property, it's to be used as a relationship, is to put it in the class of properties. Okay? So we can say MO member is a RDF property, but that's something the vocabulary does for us. Okay? Another thing the vocabulary does, as well as defining this as a property, is to use RDF schema to attach another couple of things to this property. It makes this triple, so member, this property, has a domain, according to the RDFS scheme, of music group in that same music ontology. Okay? This says, if you use this property to relate things, then the subjects should be music groups. Okay? The corresponding property is used in this triple, so the music ontology's member relationship has a range of agent from FOF. Okay? It says the objects to this property, when you use it to specify relationships, should be in the class of agent, which is a bit more general than person in FOF. So, in fact, you can have automata in groups, apparently. An interesting point of note, before we talk about the inference that's used here, so we've talked about the expectation. This thing's a property, so it should be used for relationships. What kinds of things should it relate? It should relate music groups to agents who are in that group. Okay? Interesting thing to note is that we use different vocabularies in defining this. So the music ontology doesn't just relate its properties and classes together. Here, it relates its property to a class from a different ontology. Because, again, as we said before, FOF is generic. So instead of redefining what an agent is, what a person is, the music ontology will just point at FOF. Now, if we have things in the schema, so here, for instance, we have music group in the music ontology scheme is a subclass of a class called group in FOF. Okay? From a programming understanding, we might understand that subclasses mean anything that's in the subclass is also in the superclass. And that's what we get from inference. That's one of the types of inference we get in RDFS, in RDF schema. So if we say that this particular resource, representing the Beatles, is in the class of music group, we have inferred that the Beatles are also a type, in the class of general groups, general groupings of agents according to FOF. Okay? So the schema says we have this subclass relationship, our data says the Beatles are a music group, and we get inferred this extra triple that nobody explicitly asserted that says the Beatles are a general type of group as well. Now, RDF schema as a whole has a bunch of resources that are used in inference. Okay? So there's a class called resource because everything's a resource. There's a class called literal because some of those resources are literals. There's a class called data type because we can attach data types to literals. There's a resource called class. Okay? Class is a class. It's the class of all classes. So if a resource is a class, groups other things, it itself goes in the class called class. We have the property we just saw called subclass of that relates subclasses to superclasses. We have corresponding a way to relate properties to one another called subproperty of. Now, the particular kind of inference we get is we say a subproperty is a more specific relationship. So if you're related in a more specific relationship, you're also, by inference, related in the more general relationship. We already saw properties called domain and range, where we say this is the kind of things that properties relate. This is the kind of subject that they relate, and this is the kind of object that they relate. And then we have a class, which as a caveat comes from RDF, not RDF schema, called property. That's the class of all properties. Okay? RDFS, the schema language, also gives us some stuff that's not used in inference. So we saw label to attach an identifying piece of text to something. We also have a way to relate a longer piece of text to something, just like the abstract predicate that we saw before, but in a more general way. We can attach a comment to a resource and expect it to be human-readable text. Now, we can also relate things to documents. We can say, see also, so look up another document. The object will be an identifier, which we resolve as a document, and we may find more RDF there. We also have is defined by. So a lot of the things that we define, the classes and the properties, we might want to say that they're defined in the scope of a particular document. So that can be useful. Now, a very quick word about the ontology language that extends this. It gives us a richer way to talk about classes and properties. In general, we can say that in the revised version of OWL, there are different fragments called profiles that add a different amount of power to what we expect from RDF schema. Later, we might talk about what distinguishes these, but really they're oriented towards particular ways of implementing the reasoning for you, because it comes at a cost. Okay? RDFS gives you some triples from the triples that you've asserted according to your schema in quite a low-cost way by adding more complicated ways to specify classifications and relationships, so classes and properties. We can, for instance, pick this dialect, which has EL, part of OWL, which has only those OWL properties that have quite efficient implementations in terms of the size of the model, or we can say we're implemented on top of a relational database and pick the QL profile, or we're implemented on top of a rule-based system and we have the RL profile. But in general, the kinds of things, the kinds of features from OWL as a whole in this DL part that we deal with can be understood according to these groupings. We have class construction, where you say, given some classes, I'm going to define new classes which are populated by inference. So things belong to this class according to those existing classes. We can also infer new relationships between things. So we can construct properties, okay, and say that something's related in this property according to their classification and relatedness. We can give class axioms that let us say useful things like two classes are disjoint from one another. You can't have a resource in both of these classes at the same time because they represent exclusive things. We can assign similar axioms to properties. We can say you can't have both this relationship and that relationship, for instance. And then finally, we can make axioms that relate to individuals. So for instance, we can say the only members of a given class are this individual and that individual and no others. Okay? When it comes to reasoning, the ability to assert things like this gives more possibilities, it gives more inference, but it also comes at the cost of time and space for computation. hence their arrangement into these profiles to understand what that cost is. Now, the last word in standards, at least for this part of the course, is the query language, SPARQL. I've said it's both a protocol and originally a query language, which was true of the original version. The original version gave us 4 kinds of queries that we can execute over RDF data, whether that data is just vocabularies that we've assembled plus data that we've asserted, or whether it's that plus data sets from several other locations. Everything's RDF. Our ontologies, our schema, our own data, all of the data that we collect out there from open data or from data shared from partners is all just triples. And you can understand all of those triples together as representing a big graph. Okay? The simplest thing you can do to understand the graph that you formed is to make a graph pattern to say, I'm looking for this shape in the graph. Does that shape exist or not? We call that an ask query. Given a graph pattern, or defined by a graph pattern, an ask query will tell you yes or no, that exists or it doesn't. Okay? Now, in finding matches for a graph pattern, there are holes, we call them variables, where we say, we don't know what goes here in the pattern, but the query should be able to tell us what resources can fit those holes. We say can bind to those variables, just like in other query languages. Now, there's 2 things we can do as a result. We can either say, okay, tell me about those resources that you found, those bindings that you found, as a graph. And the easiest way to do that is with a describe query. So we say, look through the graph, find where the pattern matches, and give us a graph telling us about what fits into what binds to the variables to make the pattern fit. Or we can do a select query, much like the query language SQL, SQL, on which SPARQL was based. We can say, give me a table representing those bindings. Okay? Now, it can be useful to get a table as the result of a graph, or a relation, we say, mathematically, as the result of a graph. Relations can be useful, but also often, because our understanding of the data is as a graph, and we want to find parts of it and analyze it in that same mindset using graphs, instead of doing a select query, we might do a construct query. Okay? So unlike describe that just says, give me some graph about the bindings, we either say, give me a table of them, or give me a graph of them of particular form. So with select and construct, we can say, okay, this is what the table should look like. This is what manipulations you should do. Or with construct, this is what the graph should look like. This is how you should manipulate those bindings into a graph. So just a quick word about select, because it's the familiar form. It's the one that looks like SQL. Okay? And like SQL, we can say select and have a subset of our variables, or an asterisk for all of them. We can, if we want, say from. Okay? In SQL, you always have to say from which tables do you want to join. In SPARQL, you don't have to, because the default thing to do is just to put all your graph, so all of the graphs that you get from different documents together in one big graph and query across the whole thing. So we have an optional from clause. We have a where clause, which in SPARQL is where the graph pattern goes. And then finally, you have modifiers like, for instance, order by, just like in SQL. So a really quick example. If we want to find out about albums that were made by the Beatles, we have this identifier that we've seen throughout for the Beatles. So in the where part of our query, we use that as the subject to a statement. Okay? The predicate made from FOF, that's one way to relate things that people have made, products, to them. So we say the Beatles made, but instead of specifying the object, we use a variable. We say, you tell me what the Beatles have made. Okay? But using that same variable, we say in a second triple, whatever you tell me must also have a relationship with this defined by this predicate, which is title. So it should have a title, and again, we use a variable to say, you tell me what that title is. Okay? Then after a semicolon, we say, this same thing that the Beatles made has to have tracks on it according to the music ontology. So the predicate is track, but we use a variable for the object. Again, you tell me. And then using a final triple after a full stop, we say that track also has to have a title. Okay? And then in the head, in the select part, we say, well, actually, we're not interested in the URIs for the album and the track, respectively, album and track. We're interested in the titles that are attached to them by these two triples. So please just give me back these literals. And you get back a table, one for each variable, where you'll have literals in each one, the album name and a track on it. An album name and a track on it. According to this constraint, the album has to have been made by the Beatles, and the album has to have the track on it according to that track relationship. So just to re-summarize what I said, SQL is all based on relations. A relational database defines what the relations are, combines them through joins, and gives you back a relation. A Sparkle select query is based on graphs, on labeled directed graphs, and either based on a default graph, which combines everything together, or some subgraphs, which we'll talk about in the next module, you get back a table, a relation. Okay? So from relations to a relation in SQL, in Sparkle, select lets you go from a graph or a set of graphs to a relation, whereas construct more uniformly goes from a graph, the default one, or a group of graphs into a graph. Okay. The revision to Sparkle, remember I said it's the first version, 1.0, that defines all of those types of queries. The 1.1 revision to Sparkle also lets us build updates, so we can specify how to change the graphs that we're operating on. So for instance, we can add data to them, add triples, we can delete triples, we can use pattern matching in a where clause, just like in those other types of query, to specify data that we want to either remove and or insert. And we can also manipulate the graphs that we understand. Okay? So again, this will come up more in the next module, but we can separate subgraphs and give them particular names, and then we can operate on those. So we can load data into particular name graphs, or we can move them around or clear data out of one graph without affecting the rest of the triple store in general, we would say, storing RDF. Here's an insert update, which we can execute using Sparkle 1.1, but we'll come to that in the next module. So in the next part of this webinar, we're going to talk about linked data and how those technologies just described, RDF schema language, its ontology language, and its query and update language, can be used together to explore and understand data.